So, hey everyone, my name is Steve Lorello, and I'm going to be presenting to you a brief introduction to computer vision using .NET. So, of all the topics in computing, computer vision is probably my favorite. With it, we get to take a set of pretty abstract mathematical concepts and apply them to something that's actually really quite useful and powerful. Now, if you ever dabbled in any raw computer vision techniques, you're probably like me. You mostly use either Python or C++. Both of those are boundlessly useful, but there are potential limiting in what they allow you to do with their client-side application. And that's why I'm so excited to start exploring its applications in .NET. So a good place to start is to ask the question, what is computer vision? And to answer that question, I'm going to borrow a quote that my computer vision professor in grad school borrowed from another CV researcher. The goal of computer vision is to write computer programs that interpret images. Now, there's two concepts that we need to unpack here. What are we interpreting? And maybe first, and more fundamentally, what is an image? So here's a bit of an agenda of what we're going to be covering. First, we're going to be tackling that existential question. What is a digital image? Then we're going to be looking at a little bit of hello world code using OpenCV and .NET. Then we'll start diving into that interpreting part of our definition. We'll look at convolution and edge detection. Next, we'll look at facial detection, and then we'll explore doing real-time facial detection. And with that, we're actually going to use my company Vonage's video API. And finally, we'll do some feature tracking and some image projection. So for our first question, what's an image? So here's an image of my muse for this presentation. My dog Zero. Get used to him. You're going to be seeing a little bit of him throughout this presentation. So what is a digital image? A digital image is at its most basic fundamental form a function. That function denotes a quantized sample of intensity values by position in a two-dimensional grid. Those intensity values, you might have heard them referred to as pixels, just denote light intensity along arbitrary ranges. For example, the range of a byte, 0 to 255. Now, there's no rule that say they need to fall along that range 0 to 255. It's just a convention. And oftentimes when you're looking at grayscale, those numbers will be on a range of -1 to 1 or even 0 to 1. But technically, these values can lie along any bounded range and the math will still hold. And actually, when you get into other applications of image processing, like, for example, high dynamic range or HDR, the range of values is exponentially larger and technically infinite. So the image of Zero we just saw is a matrix. You can think of it as a matrix of size n by m by 3, where n is the height, m is the width, and 3 is the number of channels. And a channel for our purposes here is just a light intensity for a particular color. The one you're probably most used to is red, green, and blue. So this picture of a pepper is a classic example of looking at an image. Now, if you look at the red line here, you could actually look at it as an image, as a one-dimensional image. So now grayscale makes things a lot easier to think about, but all the math abstracts out to multiple channels. So take a look at that red line again. It's drawn right through the pepper. You can think of that as its own image with only one dimension. And that image is denoted by light intensity values on the right, with the darker spots having lower intensities and the brighter spots having higher intensities. Now, this insight becomes really powerful. And we're actually going to look at a little bit later how we apply that insight. But I want you to first think very briefly about where are the edges in this image. Are they in the peaks of our 1D image? Are they in the valleys? Or are they somewhere in between? So now we're actually going to get into the crux of the topic of this talk, actually using computer vision in .NET. So in this talk, I'm using OpenCV, which stands for Open Source Computer Vision Library. As the name suggests, it's an open source tool. It's pretty widely adopted. There are other tools that do essentially the same thing as OpenCV. MATLAB and Octave are examples. They both have a lot of image processing functionality, but I like OpenCV as, for the most part, it's free to use. The docs are pretty user-friendly, and they do explain, in addition to how to do individual things, as a bonus, they also add on top the mathematical insights behind what each function does. Now, MGUCV is the .NET OpenCV wrapper that we'll be using. It's widely available for the .NET framework and does enable you to do quite a lot. There is, for the most part, a one-to-one mapping between OpenCV and MGUCV. So most things that you can do in OpenCV, you can also accomplish with MGU. Now, I will note that if you're like me and you've used the Python OpenCV library in the past, you might need a little time to adjust to MGUCV, as it's much closer to the original C++ implementation of OpenCV. And just to note, they do use a dual open and open source and commercial license. So to actually use OpenCV, we're just going to create a new project. For now, we're just going to create a basic .NET Core console app in Visual Studio. And then we're going to install the MGUCV runtime package manager, or package with the package manager. So now let's add a little bit of code to MGUCV. Let's add a little bit of code. MGUCV is structured around a set of static functions in the class CV invoke. And here we're using 3 of them. Note, I've stored the image of 0 in my resources directory. I named it 0.jpg, and the file is just going to be copied down to the build directory when I run this. Thus, I'm just assuming it's going to be there. The first line here reads the image of 0 into a matrix. As you're doing this, there's 2 things to note. First, the matrices are by default in the BGR, blue, green, red space, rather than the RGB, red, green, blue space that you might be used to thinking of images in. All of these structures implement the iDisposable pattern. Thus, if you want to limit the scope that the memory is being used, you can just use a using statement, or you can explicitly dispose of them after they're cleaned up. But the garbage collector when the garbage collector determines that the object is no longer in use, it'll simply call the dispose function itself and free you from the need to do anything with it. The second line creates a window with the title provided by the first argument and displays the image from the second argument. And the final line is a wait key. This is similar to a console input. It just waits for you to press a key when you're focused on the image window. And without that call, the image would just disappear and you never get to see it. So I guess I'll just pop out to my first example here. So this is that same program that I was just referring to. As you can see, it's doing exactly, sorry, let me just pull this over here. As you can see, it's doing exactly the same set of functions that I was talking about before. And if I just run this, it pulls up an image of 0, a little bit to the right on my screen, but it's right there.
Steve, what NuGet package?
Say that again?
What NuGet package did you use?
I used mgu.cv.runtime.windows.
Okay. Is it like a standard .NET, or is it .NET Core? Like, what is the?
I think it uses .NET Standard. I'm not 100% sure. They just released a new version of it. Hold on, let's look.
Okay, no problem. Just checking. Please proceed.
Okay. So here's the result. Like I said, here's the result of a little program, right? So the next topic I want to cover is convolution. Convolution is the process of combining 2 functions to produce a third. When we're working with images, this generally means taking a large matrix, an image, and running a small matrix, a filter, or a kernel over to produce a third matrix, which we usually call a feature image. And that's actually where we're going to get a bunch of our insights from. So this is essentially what's happening here. Notice the shaded region of the image. It's the same size as the filter being run over it. That's because that 3x3 submatrix is being dotted against the filter to produce the feature in the feature image. So if you trace over this filter is being centered right here, and this submatrix right here is being dotted against this, and that produces this 51 over here. So if you run this operation successively over the whole image, like that, you'll actually get a full feature image as your output. And typically when we're done filtering, we do divide by the sum of the kernel and store that value. So 51 would really be 4 in this case. Now, I'd like to illustrate why convolution is such a powerful tool. We can do some really neat things with it. And to accomplish these things, the only thing we need to tune is the kernel. This kernel that I'm showing you right here is called a Sobel operator. That operator enables you to do something really critical, edge detection. Now, remember that pepper image that we looked at earlier? Remember when I asked you where are the edges? Are they in the peaks? Are they in the valleys? Or are they somewhere in between? Well, the correct answer is actually in between. If you at some point took or can even recall calc from school, you might remember something called a derivative. A derivative is just the rate of change between 2 points on a function. It's slope. And it's the derivatives that the Sobel operator is going to calculate for each pixel in the image. Remember how I said convolution is combining 2 functions or images to produce a third? Well, that's exactly what we're doing here. We're combining our input image and our kernel function to produce a third function or image. And that image is showing the magnitude of the derivatives, which are also known as the gradients, and maybe more clearly referred to as the edges of the image. Now, there are 2 commonly used Sobel operators. The first one, the one on the left, operates on the gradients in X, and the second one, the one on the right, operates on the gradients in Y. And after you combine the 2 output feature images from those 2 Sobel operations, you get your full gradient image as the output. So here he is again, my buddy Zero, and his Mr. Rogers sweater, as I like to call it. Notice all the edges in the image. When you think about it, those edges, the places where the color is changing really rapidly, is really where we're getting most of the information of the image. The flat surfaces like the floor, the wall, they don't really tell us that much. It's where everything is kind of changing really quite rapidly. And after running convolution with the Sobel operator over the image of 0, we're actually left with a gradient outline of all the edges in the image. Those are the parts that are really bright in the output image. Now, this operation, convolution, has a wide array of applications, particularly when it comes to feature detection. And we can actually leverage convolution pretty heavily in something else you might have heard of, a convolutional neural network. And that's a topic for a different day. I'm not going to get into that in this talk. So if you want to calculate the Sobel gradients of an image, here's the process. Now, I'm assuming when I'm reading these in that I'm reading images in as color images. Not the best assumption, but just for this simple program, it holds. Now, the first thing I need to do is actually convert the color image to a grayscale image. And that's what this first line here is doing. Oh, sorry. It's I've already defined a matrix called gray that I'm going to store the output image in. I've also defined grad X, which is gradient X, grad Y, which is gradient Y. And then these absolute grad X, absolute grad Y, and the Sobel grad where it's going to end up. They're just newing up new matrices. It doesn't really do anything particularly special. But this first line here, CVT color, actually allows us to convert images between different color domains. So in this instance, we're going from the BGR domain, blue, green, red, to the gray domain. So the next thing that we do is a Gaussian blur. You're going to see quite a bit of this if you're looking at image processing techniques, and I'll explain later what that's doing. But it's really just blurring an image. And that's actually a really good thing for us. Now, the next thing we need to do is actually calculate the Sobel gradients in X and Y. So the arguments for this are the gray image, which is the source image, the gradient matrix that we're storing the output in, the depth type, which is the data type that we're actually storing it in. In this case, I'm using a 16-bit short, as opposed to the 8-bit unsigned integer that the grayscale image is in. And the reason we do that is because when we're performing that convolution operation I just referred to earlier, we're actually going to overflow some of our, some of the pixels in our matrix, and we don't want to lose any data that when we overflow it. The next two items here are the factor in X and the factor in Y. To calculate X gradients, we send a X factor of 1. To calculate Y gradients, we send a Y factor of 1. And finally, we pass in the kernel size. Now down here, we're actually scaling that 16-bit unsigned integer array matrix back to a 8-bit unsigned integer matrix. And then the last thing we need to do is actually add these two gradient matrices together. And we give them an equal weight. That's what this 0.5 is for. So we add them together, weighted, and we get our final output image, our full Sobel gradient. So here's the actual gradient of the image in X and the gradient of the image in Y. Notice how they're actually pretty different from each other. The X gradient shows the vertical lines as most prevalent, whereas the Y gradient shows the horizontal lines as most prevalent. Now, this might sound a little counterintuitive to you. X is the horizontal direction, so it shouldn't show horizontal gradients, and vice versa with Y. Well, it actually makes perfect sense because the gradients are being calculated perpendicular to the edges of the image. So naturally, X produces the Y gradients, and Y produces the horizontal gradients. And here it is again, our final result. Notice how you see both the horizontal and the vertical lines showing it pretty nicely. It gives you really a pretty good idea of what's going on in the image without any of the color. Basically, none of the energy from the original image. It's just the energy where the color is changing very rapidly. So now, let me pull up this demo. Sobel. Again, here's that same code that we just saw. If we run it, we get the image 0 as a grayscale image. Then we get the image, the X gradient image with its vertical lines. Then we get the Y gradient image with its horizontal lines. And finally, after we merge the two of them together, we get our full output image, the image of 0 that has just the edges of the image. So I just mentioned to you this, but probably the most ubiquitously used kernel is the Gaussian kernel. Lots of operations in computer vision will run what's called a Gaussian blur over an input image prior to using it in other computer vision functions. Just for example, the Sobel operation we just used. Now, Gaussian might sound a little bit familiar to you if you've ever taken statistics. It's another way of saying the normal distribution or a bell-shaped curve. We start with some center mean value. In this case, it's the center value. Down here, we're looking at 4. And these values are going to be the weight at which we're giving each pixel in the filter. So we start at some center mean value 4, and the further we get away from the center, we drop off the weight that we're providing those individual pixels when we're filtering the input images. Now, one of the things that really confused me when I first started learning about computer vision was why blurring is so useful. The reason it's so useful is actually because digital camera sensors, they tend to have a lot of noise to them. And even a little bit of noise can really throw off a lot of these techniques. But blurring images, which may make them a little less detailed to our eyes, actually smooths out a lot of this noise and makes these images more perceivable to our programs. So to illustrate this for you, and why it's so important to do Gaussian blurs, let's look at these two images. So that's our image of a pepper again on the left, and an image, of course, of Einstein on the right. Now, both of these images have had artificial noise added to them. Now, because we've enhanced the noise in this, that noise is really obvious to our eyes. Whereas if it's straight off of a film or a digital camera sensor, it might not be immediately obvious, but it does exist. And now think about how our edge detector that we just looked at, the thing that's trying to find the change between pixels, is going to work with these two images. It's going to work pretty badly, you'd imagine, because while we can still perceive the detail in these images with our human eye, the oscillation between the pixels is just too extreme for our programs to gain any meaningful insight over where the edges in the image are. So another filter that does something really useful is a sharpening filter. A sharpening filter will tend to magnify the center pixels. And it'll do that by giving a large upweight to the center pixel, and it's subtracting a lower weight away from the outlying pixels. And you can actually take that blurring operation we just did and invert it to do the same thing. So take a look here. We've actually taken our input image and run a Gaussian blur over it. Then we take that blurred image and we subtract it away from our original image. And we multiply that difference by a factor. And that actually produces the detail of the image. And then we can add that detail back to the original input image to sharpen our image. So now let's step through here. See here, we're going from our original to our blurred image. Now, like I said, blurring makes it lose detail to our eyes, but it gains clarity for our programs. Now, see on the left here, our detail image, which is the enhanced difference between the original and the blurred image. After adding that original image, we get a nicely sharpened image that we see on the right here. Now, it's probably easier if you just look at these by comparing apples to apples. See here we have the original image, and then we have the sharpened image of 0. You can see the differences in sharpness here. And you can tune the degree to which you multiply that detail to increase or decrease the sharpness of the image. But if you overdo it, you'll actually wash out the image. You'll see a lot of weird artifacts added to it. So for example, this is a image of 0 where I took that detail, I cranked it up to 10x, and then I added it back to the image. And we get these weird washed out artifacts in here. Looks very odd. So now we're going to move on to something else that's really cool, face detection. And using OpenCV, we can actually run face detection in real time on multiple video streams. So we're going to be discussing a technique for facial detection developed by Paul Viola and Michael Jones, which is actually really robust and really rapid. Now, we'll take a look at, we're going to first look at these little masks called Harlight features, which we'll see in a minute are just simple little shapes. And with them and an integral image generated from our input image, we'll determine the relative shading of different regions in the image. And after combining a lot of these Harlight features together, we can build a cascading classifier to perform facial detection. So these Harlight features, as they're called, are simple black and white images split into 2, 3, or sometimes 4 different rectangles. Now, they may look like silly little shapes to us, but they're actually extremely useful for running all sorts of detection algorithms. But in this case, we're going to be looking at them specifically as they're applied to facial detection. So 1 or 2 of them by themselves aren't particularly useful for image recognition. But hundreds or thousands of them applied at varying scale to the same image against a really well-tuned model can produce a very robust result. And more importantly, it can produce really fast. I mean, it can run on real time on multiple videos with low overhead fast. But now you might be asking yourself, you have to run hundreds or thousands of these at the same time. You have to sum up and subtract all the pixels under each region at varying scales. How could this possibly work performantly? And the answer to that is actually at the core of the Viola-Jones algorithm, the integral image. And we thought that we were done with our calc terms. So if you recall what an integral is, or if you ever learned it at some point, all it means is the area under a curve of a function up to a certain point. And that's exactly what these are. These images, they represent the sum of all the pixels above and to the left of each pixel in the image. Now, what does this do for us, you might ask? Well, the hard-like feature we were just looking at before requires us to sum up all the white areas in the filter and sum up all the black areas in that filter, and then find the differences between those areas to find the relative shading for each feature. Now, each summation is on an order of n by m, where n is the height and m is the width of the feature. Now, this might be acceptable for one feature, but this algorithm requires us to run lots of them to robustly detect faces. So this diagram right here illustrates how the integral image makes the algorithm so much faster. To find the red rectangle, which could be representative of one of our hard-like features, we only need to take the bottom right-hand corner of our integral image and subtract the bottom left-hand corner and the top right-hand corner, and then just add back the top left-hand corner. And that's it. Remember, we've summed everything up and to the left of each point in this image. So this is this whole rectangle right here, the summation of all of this. That's point D. Point C is everything to the left and above the rectangle. Point B is everything above and to the left of the rectangle. And A is the point A is the region that's going to be double negated by subtracting C and B. So with this, we can actually turn what would have been an m by n calculation, n by m order of magnitude operation into an O1 operation. And with this, we can quickly calculate the relative region in these relative shading in these hard-like feature regions. And with that and some other ML techniques, we can correlate them all together to build a classifier that will swiftly and robustly detect faces in an image. So how does this apply to our .NET programs? Well, it's actually quite a bit easier than what I just described. OpenCV has a large collection of hard-like features prearranged into a model for a cascading classifier. This model is available in just an XML file that can easily be ingested using MVCV. And with that model ingested, we can construct a cascading classifier, and then it's just as easy as running a detect method and drawing a rectangle around the detected faces. And here it is. This is all you need to do to run a face detection in .NET. You need to build a classifier, that's that cascading classifier. And with that, you're reading in this hard cascade frontal face default.xml. That's just the standard library that's just the standard XML file that OpenCV has that I just downloaded. And then you read in your image, you run detect multiscale. I pass in a minimum face size that I want to detect in this, and I will tell you in a little bit why I did that. And then for each face in faces, I just draw a rectangle on the image of the region where the face is. So this produces an output sort of like this. You see it detected my face. So the reason I actually set this before with a 300 by 300 min size is because this thing is in variable scale. And when I ran this originally, the bobblehead of Roger Clemens up there was detected as a face in the image. It didn't pick up Jorge, and the reason it didn't pick up Jorge, I think, is because he's tilted a little bit to the left, whereas Roger's looking directly at the camera. And that's because his algorithm is actually not invariant to tilt or rotation. Now, also remember, one other thing to remember is this is not photomically invariant either. So like if you have like a large shadow cast on half of your face, it might not be able to detect your face either. So let me show you this demo too. So this is that same code again, and I'm going to drag my face over here. It's exactly as advertised. It's really that simple. So transition back over. So now we're actually going to look at the same technique, but applied to real-time video, just to see how powerful this technique is. And we are going to use that using my company's video API. So we're going to create a WPF client app, and we're going to add the OpenTalk client SDK. That actually enables you to add video conferencing to a WPF app. And then we're going to add a new class implementing something called the iVideo renderer, which is an interface that's provided by the OpenTalk client SDK. We're going to call that face detection video renderer. That's going to be extended control, because it's going to be a control that we're going to place on our main XAML file. We're going to place one of them in the bottom right-hand corner of the layout. And that first one is going to be where the publisher video is going to go. That's the video that's coming from my machine and going out to the conference. Then we're also just going to add a detect faces and a connect button. We'll use those later. So now we have the main window set up. In main XAML CS, we're going to construct a publisher and a session. Now ahead of time, I've gone ahead and gotten an API key and a session ID and a token. The API key is tied to Vonage Video API's account and application, and the session ID can be generated using one of our SDKs, and you can also generate the JWT the same way. So they can all be generated dynamically. I'm just hard coding them here for the sake of simplicity. Notice how I'm constructing the publisher here and passing that publisher video element that we were talking about on the UI. And that's actually where the video is going to be displaying for the publisher. So next we need to manage the connection to our video call. When a user presses the connect button, we'll flip the connection state of the session. And if it's already connected, we will unpublish the video and disconnect. The next step is when someone pushes the detect faces button, we're going to, for a lack of a better term, start detecting faces. And we do that by toggling face detection in the face detection video renderer for each of those controls that are on our WPF, in our WPF app. Now this function is where we're going to register our on-stream created event callback. Now the on-stream created is called whenever somebody new enters the conference and they add a stream to the conference. And this is going to create a face detection video render for that inbound stream, and it's going to tell us to subscribe to that stream. So now that we have a layout and session initialization working, all we need to do now is manage the actual real-time face detection and displaying of our boxes. So by having our face detection video renderer implement the iVideo renderer, we're actually going to get each frame as it comes into the renderer. We're going to intercept each frame and run face detection on it. Then we're going to draw a rectangle on each frame to show where the face is. And finally, we're going to render the frame. So here's the beginning of our render frame function. Remember, this is going to be called each time one of these face detection video renderers gets a new frame. We're going to create a new writable bitmap. And that's what we're going to end up doing our face detection on. And then it's also what we're going to be using for drawing when the time comes. Drawing on the canvas, drawing the image of the canvas. So essentially, all we're doing here is creating a bitmap, setting the image source of the brush for the canvas for that control to that bitmap. And this effectively means that we now have access to the image, and whenever we change it, we can actually draw it on the video bitmap and have the thing display in our WPF app. So the next thing we need to do is marshal the buffer from the frame into the image. So if we're detecting faces, we're going to do just that. The image is constructed as a BGR, remember, blue, green, red, byte image. BGR is the color space that it's in. Byte is the data type that we're using, which is a 8-bit unsigned integer. We're passing in the frame, the length, the stride, and the buffer, of course, and that's actually going to bring that image into our OpenCV space. The next thing we're going to do, I have some code in here that's complicating this. I have essentially a blocker. If it didn't pass a certain interval to not run the face detection, now what I found is this ran in real time, so I actually didn't need this. I have a reducer, which I did need. So what this does, resize, is it scales the image down to a particular scale factor. In this case, I'm using 1/4, and I found that that was plenty to run in real time without any negative consequences of like having a reduced image. And then I'm going to add the image to this images concurrent stack that I have. And the reason I'm doing this and I'm not running this synchronously with the rest of this program or with the rest of this function is because we specifically don't want to run this operation on the main thread, which this would have to do. So we're going to put this off on a different thread. And then the last thing we do is we actually draw faces that we get from our faces collection on the bitmap. And then, of course, we're going to render it. So meanwhile, this bit of code is spinning on in the background. This is actually where the faces are being detected. Notice how we start this in the thread pool. Like I said, we want this operation to run on a completely different thread from the main operation so that nothing is blocked. I use the blocking collection, which is under the hood using a concurrent stack for this images collection right here. Every time I call take on this, I'm passing in a cancellation token so that if the operation is canceled, it just exits gracefully because it's caught by this. But essentially, it blocks on this whenever it's waiting for a new image to come into the stack. And we use a stack and not a queue in this case because the most relevant and the most recent images are one and the same. And then we run our detect multiscale on the image. And that actually gets all the faces for our faces collection. Now, when we detect faces, we're going to drop into this function and draw rectangles on the bitmap. Note we need to scale up the x and y coordinates back to the scale factor that we reduced it by. So I had to multiply these by 4. And then for some reason, I needed to, this was funny, I tried to use the standard OpenCV rectangle function, and that didn't work. And because it was corrupting the bitmaps for some reason, so I had to use this extension library with drawing. And that, for some reason, rendered all the x coordinates in points and all the y coordinates in pixels, which I thought was very odd. But so I had to convert the points to pixels with these. And then I just draw 4 lines on the image to actually get the final rectangle drawn around the face. So now, like I said, this ran in real time. Well, this runs in real time. I'll show you in a minute. With the scale factor reduced by 4, and I didn't see any degradation in the quality of the results that I was getting. And by real time, I mean it was running in 5 to 10 milliseconds per frame. Now, when you're talking about video chat, your best case scenario is usually 30 FPS. And 30 FPS is 33 milliseconds between frames. So 5 to 10 milliseconds per frame is effectively real time. So let me show you this real quick. Just go to this section, pop back over here. And this is that face detection video renderer I was just referring to. Now, I have another video call running in the background here against our playground. Oh, wait. Let me shut off my camera in OBS real quick so I can actually display this to you. Deactivate. Okay. So here I am again. Connect. There I am. I'll detect faces, and as you see, it gets my face. You can find my face pretty easily. Now I have other models loaded into this thing in addition to just the standard default frontal facing one. So if I turn my head in profile, the default one wouldn't be able to pick up profile, but I have a separate profile model running in this thing too. So it picks up the profile image. There's also one for eyes, and you can construct them for a bunch of different things. See, that's it actually running in real time. Let's pop back over to my slides. So for our last bit, we're actually be covering something, some pretty important concepts that are going to that'll work as a basis for all sorts of really important things like panorama and even augmented reality. And that's feature detection, tracking, and image projection. So the first thing we're going to need to talk about here is what defines a good feature. This isn't something subjective. We need a concrete definition for our programs to understand what they're going to be looking for. Then we're going to use an orb detection method for detecting these features in images. And next, we'll use the descriptors that we get from those that detection method to actually correlate features between images. And that'll all eventually lead into image projection. So now what's a good feature? So let's actually step back a second and talk about what a feature is. So a feature for our purposes is something that's going to allow us to correlate. I just realized I haven't turned my camera back on. To correlate images or correlate points between images. So if you're looking at a scene from slightly different angles, you might have a slightly different image between the two scenes, but it mostly has the same points. You want to have a way to actually correlate those two images and see where the overlap is. And that's where features come in. So a good feature is a section of an image that has multiple edges running through it. Now, why is that? So think about it for a second. If you're comparing two images to each other, if the color of the neighborhood that you're looking at for a feature, it's like a tiny little point in the image, is one color, just a flat surface, you can't really distinguish it from anything else in the image or any other place in the image that has the same color. And consequently, when you're looking at a different image of a similar scene, it's the same deal. You can't necessarily differentiate it. Now, if you're looking at something that has only one edge in it, that's a little bit better. But anywhere, any neighborhood along this edge, it's going to look exactly the same as any other part of that neighborhood. But then finally, if we're actually looking at something that has multiple edges, a corner, for example, where two edges are coming together, well, in that case, we can actually distinguish it. We can actually say like, oh, well, this corner appears in this image. Now I have a very similar looking feature over in this other image that I can correlate. So we're actually going to use the orb detection method, which stands for oriented, fast, rotated, brief. It's a compound acronym. I don't remember what fast or brief actually stand for, but it's a compound acronym. And the reason I use orb is it's free. Other feature detection methods like SURF and SIFT are patented, so you usually have to pay the creators for them. If you want to get the upgraded version of CV, OpenCV, you certainly are able to. So this bit of code here is actually going to perform our detection on one image. So we knew up an orb detector. We pass in the number 10,000. 10,000 is the number of features that it's going to be shooting for to find. Then our feature set is going to be in this vector of key points, just key points in the image, and the descriptors, which are really describing each feature, that so we can use it to correlate between different images, is just going to be a new matrix. And then we run this detect and compute method. We pass in the image, we pass in the features vector, we pass in the descriptors matrix, and then we just draw the key points between the two images with this nifty little features 2D toolbox, which OpenCV comes with. And as you can see, it highlighted, the areas highlighted in this image are where kind of everything is coming together. And you can kind of see it behind me too. Like you can see the Hofbrau Beer House steins, like where the edges are that it's showing are, or where the corners are that it's showing, or where like multiple edges are coming together. And they can actually be correlated between different images. So the next thing we need to do, now that we've detected some features, is to run a feature match. So we'll be using a KNN, K nearest neighbors matching function, and a brute force matcher for this. So we add descriptors for our first image. That's the descriptors that we got out of the first match. We also ran a second feature detection on their second image. And then when we run the BF match, KNN match, we pass in that second set of descriptors, a matrix where the KNN matches are going to go, the number of nearest neighbors is looking for. And then we loop through that, the matches that this thing found, and if they fall within a certain threshold, a certain closeness, then we actually match them. And then we can use, again, features 2D toolbox draw matches to actually draw the matches between the features. And here's two images of me, me with my head slightly tilted. You can actually see it drawing the correlations between the images. Those are those features that are matching really well. So the last topic I really want to cover, and I'm not going to get too much to this because it gets really quite nuanced and interesting. It gets really interesting, but it gets a little more, the math gets really tricky to describe. So I'm just going to kind of go over this a little bit, is image projection. Now, to do image projection over multiple frames of an image, we need to keep track of the features between images like we were just talking about. And then we need to build these translation matrices. They're called homographies to map the old pixels onto the new ones. So this sets up a system of equations with 8 degrees of freedom. And that means that we need to find at least 4 matches between images to compute this homography, which is the translation matrix, to teach us how to convert one image to another. And that actually allows us to project one image onto another. So think about what you can do with a 2-dimensional image. You can move it around. That's a translation. You can rotate it. You can increase or decrease its size, scale it. You can perform an affine warp on it, or you can perform a perspective warp on it. And those are just all different ways of looking at the same image. Now, those transformations, if you want to actually apply these transformations between 2 different images, sets up the systems of equations that you see up here, this first matrix, this first giant matrix up here. And I'll tell you right now, you don't need to know all this. I can tell you that I don't remember the math from all this. The thing you do need to be able to calculate, and again, you don't need to know how to calculate this, you just need to be able to do it in OpenCV, is the homography, which is this little one down here, which is a 3x3 matrix. And these different points in this homography, they define all the translations that you would see up here between different images. And this last bit of code right here is just a simple little toy example. And it's going to take a picture of a cat and a picture of my face. It's going to detect my face in that image, and it's going to project the cat picture onto my face using a homography. Remember how I said that we needed 4 points of correspondence between 2 images? Well, we can get the 4 points from the 4 corners of the cat image, and then we can get the 4 points in our destination image from the 4 points of the rectangle that surround my face. And now with that, we're off to the races, and we can actually perform our projection. And there it is. My face replaced by a cat face. Now it's a bit crude, but you can get the point. Now, if I wanted to project this onto a running video, you can do that as well. You just need to keep track of the image space, like face space, that you want to project the image onto. And then as you're going through, you can just update the homography appropriately to project onto. So I hope that you enjoyed our little stroll down computer vision way. It's a really big field, and really just started nudging the tip of the iceberg of what it can do. And before I go, I just want to tell you a little bit more about me. I've been a developer for about 7 years now. Been a .NET developer for about 5 of them. I got my start working in the global positioning system, better known as GPS, and the American and UK air traffic control systems before I moved into advocacy. during my nights and weekends, I study computer perception and robotics at Georgia Tech. Go Yellow Jackets! And you can follow me on my blog and Dev2, or I also have a lot of blog posts on our company's blog, which is nextman.com/blog. You'll see a bit of a theme to my work. I like to explore computer vision and artificial intelligence, integrating them with .NET. And I also like to integrate them with our awesome APIs over at Vonage. You can follow me on Twitter at Lorello. And so just to tell you a little bit more about my company, we are Vonage. You might remember Vonage, the residential voice over IP company. We actually have a full set of communications APIs. So if you need to contact your customer via SMS or WhatsApp or Facebook Messenger or Viber, or call them, or obviously do a video call with them, you can do all of that with our stuff. I actually have an updated coupon code that I can share with you if you want, but yeah. So that's it. Here are some resources. Everything I just showed you is available on GitHub. I found the MGOCV docs a little bit unhelpful as they're really high level, but they can be useful nonetheless. As I said, the OpenCV docs are intensely useful, and if you're interested in computer vision, I definitely recommend giving them a read. Now, does anybody have any other questions?
Oh, before people have asked questions, I wanted to make sure that you shared these resources. If you can post them to the meetup page, that would be really appreciated.
Sure.
And yeah, there's a lot of good concepts in here. I think that as far as my understanding of computer vision goes, I'm like, kindergarten. So I probably need to read up a lot to even understand some of the concepts in this particular talk. Okay, I'm going to go ahead and stop the recording, but if anyone else has any questions, feel free.